Hey, okay, so I want to take a look at the Chapter 1 review problem number 8, where you are asked to find the horizontal and vertical asymptotes of f of x, which is given there, and then to sketch a graph of the function and note the discontinuities. Um, so let's take a look. Now, I'm going to write f of x out so that I'm not bothering with the little square part. So I'm going to write it like this, 5 x minus 5 times x minus 5 all over x plus 2, x minus 5, x minus 7. Okay, so there's our function. One of the things to notice here is these two terms would cancel out normally, except that you know that x can't be 5. So let's actually write the domain out first. Domain x can't be, we know in the denominator you can't have 0, so none of these individual terms could be 0. So x can't be -2, it can't be +5, and it can't be 7. Okay, so, or you could also write it like -infinity up to -2, union -2 up to 5, union 5 up to 7, union 7 up to anything else, which is kind of a long way of writing that. I prefer the x does not equal in that case because it's so much easier to write. So on the graph, you're going to have some sort of issues when x is -2, 5, or 7. So over here, I'll just start the graph. So at -2, you know some issue is going to happen here. Maybe it'll be a vertical asymptote, maybe it'll be at a hole, maybe it'll be some sort of jump discontinuity, although those pretty much only happen with like weird absolute value type stuff, things like that. We also know we're going to get an issue at 3, 4, 5, and it's 6, 7. Okay, another thing to note is if I were to actually cancel those two terms, then I'm going to get a function that's just like f of x. So this function right here is similar to this function. So I'm going to call it g of x equals 5 parentheses x minus 5 over x plus 2, x minus 7. And the way that I get this new g of x is just by pretending that I've canceled out those two terms over on the left side here that I've circled in red or boxed in red. Okay, the only difference between f of x and g of x is that g of x is defined when x equals 5 because there's no restriction on the denominator in g of x. So this one, the only difference between g of x and f of x is that g of x is that, let me do this, is that f of x isn't defined at x equals 5. Okay. So if we knew what g of x looked like, then it would be exactly the same as f of x, except I'd erase the 1 point on the graph of g when x is 5. Okay? So that means that since the only difference is that x can't be 5 in f of x, that means f of x is going to have a hole or a removable discontinuity at x equals 5. So we know that along x equals 5 here, wherever the y value is, it's going to have a hole. So the way to figure out where that hole would be is to look at the function that's just like it, except it is filled in. So the function where it is filled in, so f of x has a hole at 5. G of x is exactly the same as f, but without the hole. So if I figured out what g of 5 is, right, and I plug that in, so that's 5, 5 minus 5, over 5 plus 2, 5 minus 7. Well, the numerator is 0, so this whole thing is 0. So that means that g goes through the point 5, comma 0. So G goes right through here, right? Goes right through 5, 0. F of x is exactly the same as G, except at that point. That's the only point where it doesn't exist compared to G. So really, when I graph F, this is going to be the graph of F of x over here, not G of x. It's going to have a hole where G would have filled it in instead. Okay, so I know that my removable discontinuity is at 5, comma 0. The other two things in the denominator where the domain is messed up, so that would be here at -2 and at 7. Well, those don't cancel with anything in the original function. So that's where we would assume that there are vertical asymptotes. Those are the ones that don't cancel with the numerator. So at -2, I'm going to draw a vertical asymptote. And at 7, I'm going to draw another vertical asymptote here. So there are my two vertical asymptotes. So now if this were a calculator question on a test, then just graph it on a calculator. The only thing you're going to have to know is that there was a hole at 5, 0. Because if you don't know that, you're never going to be able to see it on your calculator because it'll be right on top of the axis. So you're just not going to realize it. So instead, so the hole is really on a calculator part of the test. That would be the part that I'm looking for the most. Did you realize there was a hole there? And if you did, then great. You can probably just sketch the rest of the graph and with no problem just by looking at your calculator screen. But let's say this was a non-calc question. That makes it way harder. So one of the things you would have to do is look at vertical asymptotes and horizontal asymptotes. So horizontal, we already have the vertical asymptotes. That's at x equals -2 and at x equals 7. The horizontal asymptotes, well, that says what happens way out when x equals infinity, -infinity, and way out when x equals infinity. So that's what we need to analyze. So let me write this out here. So the horizontal asymptotes happen when we look at the limit as x goes to infinity of f of x. And also, separately, you're supposed to look at the limit as x goes to -infinity of f of x. So the nice trick about infinite limits where x goes to infinity or x goes to -infinity is that you don't need to examine the entire f of x. You just need to examine dominant terms of the numerator and denominator because those are the things that matter when you're plugging in really big numbers and really negative numbers. So so the dominant term on top, if you actually FOILed out everything and distributed the 5, the dominant term on top is going to be, let me actually copy this here. How do I do that? Where's the selector? There it is. So I am going to, maybe I'm not going to be able to do this. There we go. So I'm going to copy this and I'll paste it down here so we can reference it easily. I have no idea which one's going to work. There we go. Perfect. Oh, I lost the line. There it is. Okay. So if you think about what the dominant term on top is going to be, I'm going to multiply out the x minus 5 squared, and the dominant term from that will be an x squared. And then I have to multiply it by 5. So I'm going to get a 5x squared. On the bottom, I've got an x times an x times an x, and then no number in front. So the dominant term on the bottom is going to be x cubed. So that's really all I have to analyze when I look at what happens when x goes to infinity. So this turns into the limit as x goes to infinity, and using the dominant terms approach, because it goes to infinity, I can say it's 5x squared over x cubed. And the only place that this graph gets messed up is at 0. So way out at infinity, I can simplify this problem. So it turns into 5 over x, like that. Well, 5 over x, at this point you can apply some analysis to it. Well, what happens if you plug in a number like 10 billion right there for x? Well, that's going to be 5 over a huge positive number. And a huge positive number that divides 5, you know, if I do 5 over a billion, Well, the bigger this number gets, the smaller the whole value becomes, so this turns into 0. So this whole limit statement, linked by equal signs, it says that when x goes to infinity, f of x turns into 0. So that means that y equals 0, that line, y equals 0, is a horizontal asymptote on the right side, since I'm looking at when it goes to infinity. Okay, so now I know I have y equals 0 as a horizontal asymptote on the right side. So up here in my graph, I will sketch a little dotted line here on the right side. Whoa. And say y equals 0, right? So just over here, it's going to be y equals 0. On the left side, so when x goes to negative infinity, it turns out you're going to use the same exact thing every time. This rule doesn't change except it'll have a minus sign there. This rule doesn't change except it'll have a minus sign there. And then, so let me write that one. Limit as x goes to negative infinity, 5 over x. So that's going to turn into 5 over a really negative number. I'll write this, really negative number, right? And if I plug in a really negative number like negative 10 billion, 5 divided by negative 10 billion, well, that's also getting closer and closer to 0 the more negative that bottom number gets. So now this tells me y equals 0 is a horizontal asymptote, and since it's going to negative infinity, on the left side. So not only is y equals 0 an asymptote on my right side, but y equals 0 is also an asymptote on the left side. So this is on the right. Okay, so now I have my horizontal and my vertical asymptotes. I still don't quite have the graph. And again, if it were a calculator problem, well, then it's easy. You just graph it, and the only trick is to remember the removable, the hole there. But let's say you didn't have that. And for this test, I probably would say use a calculator, and the only thing I'd be looking for is that. But let's say that it was a non-calc question. Well, the way you can figure out what to do around the asymptotes, because you know it's either going to do this or that and approach 0. But let's say you need to figure out, well, what happens when I get to the vertical asymptote? Does it go up here or does it go down here? So in order to figure that out, we need to do a little limit analysis of the asymptotes. So let's look at our vertical asymptote at x equals negative 2. So that means the way to analyze that is say, okay, well, let's look at what happens when x goes to negative 2. And let's first look at from the right side of f of x. So let's see. You know what? I'm not sure. Well, okay, we can analyze this. We can do this. This is going to be more for chapter 2, but if you're interested, you can take a look. So as x goes to negative 2 from the right side, I'm going to write the function out here. It's 5x minus 5 squared over x plus 2, x minus 5, x minus 7. So if you think about what happens when I plug in a number just to the right of negative 2. So a number just to the right of negative 2 on the number line would be a number like negative 1.999, ... right? So, okay, so if you think about that, then you can analyze positives and negatives for the numerator and denominator. So if I were to plug in some number just like this in for all my x's up there, then the top is going to be 5 times something squared. So that's going to be a positive number. And then the bottom is going to be negative 1.999999 plus 2, which is going to be a positive number. And then a really tiny positive number, by the way, tiny. And then negative 1.99999 minus 5, which is still negative. And negative 1.99999 minus 7, which is still negative. So I'm going to get a positive number over these two numbers, which ends up being positive, times a really, really, really tiny positive number, which makes a tiny positive number in the denominator. Okay, well, a positive divided by like a really tiny positive number So that would be like, let's say let's say the number on top is 10, and the number on the bottom is 0.000001, right? So it's a positive over a tiny positive. That is really close to infinity. And the smaller that number gets, the closer this gets to infinity. So this goes to infinity. So what we've analyzed here is that as x goes to -2 from the right side, y goes to infinity. So again, as x goes to -2 from the right, y goes to infinity. So as x goes to -2 from the right side, from this side here, y goes to infinity. So I know that this picture is going to do something like that. Okay, now you can apply that same kind of analysis to what happens as x goes to -2 from the left side. And if you do that, then instead of putting a little plus here, you're going to put a little minus right there. And instead of plugging in something like -1.999, you're going to plug in something like -2.0001. And then the only difference in the work is that that number ends up being a negative number instead. So you get a tiny negative number in the denominator. And if you do a positive number over a tiny negative number instead, you're going to end up with a number that approaches negative infinity. So then that means if x goes to -2, so I'm just going to write the final limit statement. As x goes to -2 from the left, y, or f of x, turns into negative infinity. So then way back up here, as I approach -2 from the left, y goes down to negative infinity like that. Well, I also know that it has to approach 0 way out there, so now I've finished this part of the graph. I'm not going to work out all of x equals 7 because that's just going to make this video super long. But it turns out that as x approaches 7 from the left side, this graph shoots down to negative infinity. And as I approach 7 from the right side, it goes up to positive infinity. And then you can kind of figure out, you kind of have to do a little bit of assuming, but since it goes to 0 way out at infinity, it looks like that. And then it's got to go through this point, except for the fact that it's a hole there, so you're going to just kind of guess that it connects like this, like that. And now you have the picture of your graph. I wouldn't give you one this complicated for the Chapter 1 test unless it's on the calculator part of the test. But it's definitely useful to start understanding those ideas now because we're going to do a ton of this in Chapter 2. All right, I hope that helped a little bit, and good luck studying.